Hi everyone. I'm very excited to introduce Dr. Gupta, who is a researcher at in the AI research group at Lawrence Livermore National Laboratory. Prior to this, he was a postdoctoral scholar at the University of Washington, Seattle, and an AI scientist at IBM Research. His research focuses on mining large-scale time series data, and more recently has been working on leveraging LLMs to jointly understand text and time series data. I'll let you take it away, Dr. Gupta.
Thank you, Abel, for the kind introduction. And thank you, Peter, for organizing this talk. I'm delighted to be here. So I'm currently working at the Lawrence Livermore National Laboratory. Before this, I was at University of Washington, and all of this work is from my time at UW. So the title of my talk is Do We Need Large Language Models for Time Series? And this is a joint work with Mike and Ming Tian, who are PhD students at UW and University of Virginia, and Tom and Tim, who are faculties. So do we actually need large language models for time series? No, we don't. So that's all, folks, and thank you for joining this talk. But if we go deeper, if you want to know why we don't need them, then first we have to understand the question that why is time series important? Uh, they are important because they are everywhere. So time series is in social networks, like you have posts, you have likes, you have comments, you do virality modeling of whether some tweet is going to go viral using a time series. They are in healthcare. You have hospital visit records, you have EHR, you have mental health records, and you need to model them to learn how a patient is growing. Uh, and they are in finance. You have stock prices, market trends, and they are almost everywhere. So this is what usually a time series looks like. So you have some squiggly lines. And if you have one line, it's called a univariate time series. And you have multiple lines that interact with each other, then it's called a multivariate time series. So they're almost everywhere. To give you a few examples, uh, this small line determines what's going to happen to trillions of dollars. And to forecast it accurately and to know where it will go is incredibly important. Now, we also used a time series modeling frameworks to learn what will be the amount of CO2 in the atmosphere in the coming years, and use based on that, determine what will be our green earth initiatives. So these are also incredibly important. And lastly, in ECG signals, a very minute spike are so important that modeling them using a very highly complex model is so important that even human life depends on them. So time series are important, they are everywhere. Moreover, language models are also everywhere. So they have been used to process text, and they have almost outperformed all NLP benchmarks. They can generate ultra realistic images that we never expected them any model to do. And modern LLMs like Gemini and GPT-4 can also work on videos and can also process graphs. So you can actually have a knowledge graph. You can have a graph of nodes, and you pass it to a language model. It can process it and show you the results. Uh, so one can very easily say that language models are poised to be the universal user interface. So if anyone has to interact with data, his own data or any private data, he'll probably interact with a large language model. So there will be an interface where you ask your queries, and the LLM will process the data or interact with it and give you the output. And we are seeing right now itself, because everyone almost uses Perplexity or U.com, both of which have a backed by a large language model. So you pass the queries to a Perplexity model and gives you the results. Now, LLMs can do all this stuff. They can work on images, graphs, videos, but what about time series? Why don't we have an interface where you pass your own time series and you ask questions about it? Well, why don't we have it yet? There has been some developments along this domain that a recent work by Gruber et al. Showed that if you pass a time series in a specific form of tokens, then the LLM is able to understand it. So if you pass a time series of like this, and you include separate spaces or separate commas, and the LLM is very well able to better tokenize it, and it understands it, and it's also able to forecast it in a zero shot setting. So the results are quite fascinating. And a recent work by Google also showed that if you pass the time series of ECG, for example, to the large language model, and you ask it to classify like what sort of ECG it is, it was able to do that as well. So these results are quite fascinating. That LLMs can actually understand or forecast time series. But our results and a very in-depth analysis of all these models shows that across both these tasks, the LLM was not important at all. That either the LLM did nothing, that if you remove LLM, nothing happened. And if the entire model with the LLM was compared with a very small, very simple baseline model, like moving average, the performance difference was almost negligible. So LLM is perhaps not that needed. Uh, it's a very funny incident that based on our own paper, there was a post on Chinese social media where someone said that Dracula is scared of the sun, Superman by kryptonite, and large language models are scared of time series. So thank you for anyone making this meme. So this presentation has two broad sections. The first section is where we try to answer the question, can large language models reason with time series? And our definition of reason is quite different than what we feel the reasoning for text is, because here we try to answer the question, can LLMs actually understand a time series? That LLMs can generate everything. They can generate time series as well, but do they understand it? And why the traditional time series benchmarks, like for classification forecasting, are not enough to evaluate this property. And we also try to answer the question that if we have a very standard task, like forecasting and classification of time series, can you actually look beyond that? Can we have a performance metric that's much, much beyond than just some values in the table? The second part takes a step back. So if we dive again deeper into standard tasks, for example, forecasting in this case, can LLMs actually forecast time series? Because there have been like several claims that say that LLMs can forecast. If we fine tune GPT-2, it can forecast. If we fine tune Llama 2, it can forecast. So we dive deep into, do we actually need large language models for forecasting settings? And if we need them, can we actually use them for real world settings? So these are two publications that both these threads are based on. For now, let's focus on the first part. So can large language models reason with time series? So LLMs can generate anything. So if you ask them to generate text, they'll give you text. If you ask them to generate image, they'll give you image. And if you ask them to generate time series, they'll give you some time series. But do they understand it? For non-time series folks, I would like to point out that generating and understanding time series is like you can generate jokes. LLM can generate jokes, but it has been shown in multiple research articles that it does not understand humor at all. It just generates jokes. And even if it understands time series by some extent, even if it does, how does it compare it to human performance? Like, is it actually useful? Can we actually use the understanding ability of large language models? Let's ask some questions that are beyond generation. Like, what all do we need our large language model to do? Do we only want it to generate time series? Or like we should be able to give it a time series and ask questions about it, like where did time series come from? What is happening in the time series? Like, is it going up? Is it going down? What are the trends? And since LLMs have been trained a large variety of global knowledge, it should be able to do some sort of a counterfactual prediction that if I say that some event of a time series will be changing, then how will the time series change according to that event? It does very well for images, but can it do that for time series as well? So this definition is what we try to encapsulate in the word reasoning. And since that many companies have claimed that their large language models is capable of reasoning, we consider this entire definition of understanding time series and doing some meaningful tasks out of time series as reasoning for time series. Now we dive deeper into our definition of it. So what are the tasks that we feel are necessary for any large language model to do? And we define them for it to be capable of time series reasoning. So the first task we call is etiological reasoning. So if I give you a time series and a text, any model should be able to understand or correlate that what the time series is about and how it aligns with the text. For example, in this scenario, you have a time series of, say, some sort of time series, and you have to understand that what is the right description of it, like which can be the better generator for this time series. So in this case, the values for the time series are between 5,000 and 7,500. So the first sample is daily step counts after New Year resolution, or the minutes of sunlight per hour over 2 days. So the minutes cannot reach these high values. So this is going to be the most likely answer. Coming back to what do we mean by time series reasoning? One more thing that someone or any model should be able to do is I give you a time series and I ask you some questions about it. Can you answer them? So like we call this sort of a activity called question answering, that if I give this time series and due to some reason there is some sort of a glitch, and I ask what is the overall brightness trend, like the overall trend in the time series. So as anyone can see that the trend continues upward. Yeah, it's interrupted, but the overall trend is upward. And thirdly, uh, if I have a time series and I want to forecast it, but I don't know what the next forecast will be, right? I don't have the test set example. It's a real world setting. So you only have the one time series and you want to forecast it. But you have some sort of a text knowledge of it. Like you are some domain expert and you can write in text that, okay, after some time, the time series is going to change like this. So what will the forecast be? For example, in this setting, this is the normal time series. And at this time point, we try to evaluate whether any model can predict it. And we give some sort of additional text that after 60 weeks, uh, like the mutation or some sort of a value is supposed to increase drastically. So this is what the ground truth turned out to be. And this is what the ideally the any model should be able to forecast. But if you cannot process this text and you only have this time series, usually the forecast will be along this line. So this is what we feel that are three important aspects of any model who claims should be able to do like time series reasoning. So again, we fall back to the question, why don't we have a chat GPT for time series? The chat GPT can do all this stuff for images. Chat GPT can do all this stuff for text. Why don't we have a chat GPT for time series? We did extensive research on why we don't have it yet. And we found that there is no such data set. So if I give you a time series and ask questions about it, how can any large language model answer it if it was not trained on it at all? So there is no data set for this task. And it seems so reasonable and yet so important. The reason we don't have a data set is because that the combination of time series and text together, where the text describes a time series, is incredibly rare on the internet. So you have several pages, several posts where you have images and then you have corresponding text. So therefore, you can download them or you can crawl them. You have a large language model trained on them. That's easy. But this is what usually what a time series looks like. There are too many scribbles, too many noises, and it's very tough to find someone to give you a textual explanation of what's going on here. And even if you find someone, if you find a domain expert for ECG, you find some finance expert for finance time series, you find these experts and you ask them to label them, that data set won't be enough to train a large language model. So our first contribution is that we go the prompt way, like we use GPT-4 in this case, and we have worked hours and hours on crafting very nice and tedious prompts, and it becomes a very nice pipeline for it, that how we come from normal text to an actual time series, which I'll go deeper into. Uh, so our first contribution is around 5,000 scenarios for time series. For example, this is a time series for coffee sales data. All of them are synthetic. This is some monsoon rainfall data and more so. Uh, so this time series has some sort of features, a description, and many more features as well. So this entire crafted data set, in each of the samples, we have a time series, we have a caption, we have a metadata that what are the features in this time series, and we have some characteristics as well. We have tried our best to have some sort of imitation in this time series from the real world, we have tried our best to bridge the gap between what a synthetic time series can be and what a real time series should be. And each entry has all these features. So what can you do using this data set? The first thing is that you can have your own set of tasks. So if I give you a caption, if I give you a time series, it has also has the code of what led to this time series. Can you actually have a code understanding task? Can you have a caption to time series task? Can you have a metadata time series task? Like you can have all sorts of tasks that you can train your large language model on. And this data set is completely exhaustive in this setting. It has all these features for each and every example of time series. But is it actually useful? So does the data set bring us any new thing that any standard LLM was not able to? Can we actually use this data set to have a large language model trained and do better on some tasks? So first thing that we try to do is that we use this data set and then we do some human evaluation. So we create a set of tasks, which are MCQs. So each MCQ has 4 options and we evaluate on multiple settings. But if you remember, we discussed 3 ways of reasoning. The first one was etiological reasoning, and second one was Q&A, and third one was context data generation. So in this slide, I'll probably highlight the 2 of the tasks that we tried on right now. For etiological reasoning, what we did is that I'll give you a time series and you have to select the best description. So there's 1 correct description. There are 3 randomly sampled incorrect descriptions. So as you see here, this is the screenshot of the user portal where we asked humans to annotate a time series. Like this is the time series and which one of them you feel is the correct description of the time series. The second task was Q&A. So what we do is that we have this description, we have time series, we have all this metadata. We prompt the large language model again to give us a set of MCQs for this time series. And using these MCQs, we ask humans to answer these questions for the MCQs. And then we compare like how good are LLMs. So first things first, let's try whether us humans can answer these questions as well. So this will be a very small activity, and I hope everyone would want to participate in it. So this is one time series. So this time series is a COVID-19 cases for Massachusetts. So this has been taken between 2 timestamps, which it's been July 2nd, 2023, and March 17th, 2024. And these are the number of cases. It goes up, then goes down, then again we see a spike, then it again comes down. So this is the number of cases for COVID-19 we saw for Massachusetts. The first question, when was the number of cases the highest? Around this time, right? Around this time, the cases was highest. So what's the most apt time where we can say that where we can approximate that the number of cases was highest? Since this was March, this seems to be closer to March. I would say Jan, right? Which is actually the right answer. So like any human can actually pinpoint what the right answer is. So now let's go into a detailed question, an in-depth understanding question. So what is the visual representation of this time series? So do the case steadily decrease? Are there minor fluctuations? So we obtain first peak and then things go down. Then we again obtain a second peak. Or thirdly, like everything just remains constant and nothing is observed. So C is definitely the right answer, as we can easily see that there are 2 peaks in the time series. So these are very simple questions that any human being can answer. But the question comes in, if we try to automate this process, if we have a time series and we pass it to a large language model, can any large language model, even the fancy ones like GPT-4, can answer it or not? So what do we compare this with? So we have humans, then we have a human LLM standoff. So where humans compete with large language models. So we compare with the very large models like GPT-4 and even GPT-4 Vision, where we pass the time series as a plot. We have zero shot as well as fine-tuned large language models for Llama, Gamma, both of them. And both of them have been fine-tuned for predicting the description given our input time series. We also try to do fine-tune a vision-based Llama for Lava, where we pass the time series of matplotlib as input, and then we fine-tune it to predict the right description. So everything is fine-tuned and as well as in zero shot settings. The results are quite surprising. The results are quite surprising. Is we note that even the best large language models like GPT-4 Vision and GPT-4 Text, which have all the worldly knowledge, they perform completely on like inferior to human performance. Like this red bar is actually random performance. So you have MCQs. If you randomly select any option, there's a 25% chance you'll be right. So random is here. Then you have GPT-4 Vision, which was given a time series and asked to identify what the right description will be, or the right answer to the question will be. And here is the results for etiological reasoning. We know that human beings are very easily able to adapt to these questions. Like they can answer any sort of questions you ask, what a time series looks like, what is it about. And same thing is with etiological reasoning and question answering. But LMs fail miserably. So we know that there is room for improvement. That means that our data set is actually crucial in for developing large language models, where if you pass a time series as input, you should be able to learn what's going on.
We
Uh,
have a quick question in the chat. What exactly are you giving the LLM? Is it the graph or the raw data?
so that depends on two things. For one setting of Lava, we pass the graph, and for Llama, we give the time series as text. And same is for GPT-4 Vision and correspondingly for GPT-4.
Great. Thank you for answering that.
Now let's focus on the task of context-aided generation, that given a time series and some helpful text for a time series, can the large language model actually understand what's going on? We were incredibly hopeful for this task because like LLMs can understand text, right? So they should be able to generate or understand what the future will be. So let's consider a toy example. It's a very simple example where we have a fridge temperature time series where there's a power outage. And so the temperature is recorded for each and every time. And then there's a power outage. So the fridge temperature will go up. And after when the power comes back on, the temperature again goes back to normal. So this is what usually that time series should look like. This scribble line where you have normal temperatures, outage, and then it should go down. We try to forecast what will happen in the future by selecting this time as the past will pass to the large language model, and we forecast it to give the future. Now, we have some text that actually explains that there's a power outage, something is going to happen after the power outage. So we have text as well. But first, we want to check whether any model or specifically GPT-4 can forecast the time series without the text. If I just give this time series and ask it to forecast, how does it work? Quite bad, quite bad. So as you can see that you have a time series like this, it just randomly gave you out, blurted out the exact same sort of an angle and is give you that this is what the forecast will be. But when I give a context that in addition to the time series, I give some context that there's going to be a slow decrease of temperature once the power is restored. There is a stable temperature values before and after the outage. And the overall time series has slow ascending and descending trends. So like if I give some more explanation, which I have removed from for brevity, if I give all these sort of context along with the time series data, can it forecast now? Yes, quite well, quite well. So we found that GPT-4, if we give a time series and some additional context as text, it worked quite well. But that was only for a very small set of samples. And this is one of the cherry picking ones. If we average across all thousands of time series and across all sort of scenarios and context, the performance gain was almost negligible. Like we could not actually define that do we actually need a text aided model, or if we just have a moving average of a window, moving into average, will that work better? So GPT worked better, but not by a lot margin. And there are huge details in the paper as well, like how different type of experiments are conducted and what we found out. So coming back to the question, can LLMs reason with time series? Right? Can they understand, or do we need them for these tasks? For current LLMs, perhaps not. Perhaps not. For right now, I don't think so. Now we focus on the second part of the talk, that are LLMs useful for even standard tasks that have been done since late 70s. We have been doing time series forecasting from so much time. We have ARIMA and we have so many models which are incredibly old and they perform so well. So can LLMs do that task at least? So for non-time series folks, I want to highlight that the first question comes that if you have a time series, and I showed you that there are ways to prompt it, but if you want to train a large language model on that time series data, how exactly that architecture works. So this is one example that from a recently paper by Zhao et al. Is that you have a time series, which is like incredible, like very raw time series, and then you do some sort of a normalization. You normalize all the values to be in some sort of a range. Then you patch them. Patch is a way to like compress the entire time series into like small tokens or buckets. So most people try to do it using a moving window, or there are several other techniques as well. So you try to patch different parts of the time series. Then you get an input embedding. You like embed these patches. Then you pass it to a transformer module. So which is usually a GPT-2 or some sort of a smaller large language model. And this is a way that these folks used to train, or I would say fine tune their large language model on time series. So this LLM has multiple layers, and they froze the feed forward layer and multi retention layer because it was already trained extensively. And they try to fine tune their normalization layers and the position encodings. So they say that for time series, understanding the position is much more important than understanding the contents within time series. And their model, they actually claimed that their model got state-of-the-art performance, which was incredibly big. Like you can actually fine-tune a large language model for time series. To give you some sort of a deep like understanding of what other architectures also look like. So any LLM for time series would look like this. So you have a time series, there's some norm, some sort of a instance norm, like you normalize it, there's some encoding, then you align it, the large language model with encodings with time series encodings, then you have pre-trained large language model, then you project it for the time series forecasting tasks. Now, either the LLM is frozen or trained, depends on what the architecture is. But usually the other three aspects for encoding, alignment, and projection are most likely trained. So this is the a high level overview of what several models look like. Now to understand, is LLM actually useful? The first thing that we can try to do is let's just remove the LLM. So you have a time series, you have some normalization, you encode it, and then you directly throw it to the projection. Very simple, just remove the LLM and let's see whether the performance goes down or it goes up, what happens.
Sorry, one question before you move on.
Yeah.
So I mean, it seems that the normalization, I understand why you would do it so that all time series have the same range, but you have to provide the LLM what are the ranges. I mean, like if you're measuring, I don't know, the stock market prices, that will have a particular range of dollar values, and if you're measuring something else, a very different range. So don't these LLMs pass also the ranges, both like the kind of y-axis and the temporal? Because sometimes it's maybe in the order of seconds, or once maybe in the order of days or months. How do you pass that? And if you don't pass that, that seems like a huge loss of information.
So that's actually a very good question. So when we fine tune the large language model, all the time series are in the one uniform scale. So in one data set, if I say that if I want to forecast a time series in this setting, all the samples are in seconds. And if I try to forecast something for say a different domain, all the time series are in say hours or months, whatever the scale is. And this setting is only for forecasting. So we do not provide text at all. So in the second part of this talk, we only use time series as input. So we do not provide a text at all to the time series. So there is no such thing called context.
Oh, okay. I mean, it seems like you're leaving a lot of critical information. If you, in the question answering case that you were doing earlier, how would you know what the time series is? But you may have two time series that look similar, but they have vastly different scales, both on the magnitude of the value, which is a univariate time series, and on the time scale, I mean, it could be anything. So
for question answering, we provide we do provide this metadata information. We provide the metadata. But for forecasting, we do not provide that.
Okay.
Thank you. That's a very good question. Thank you. So in addition, this is what the normal architecture for LLM for time series looks like. So you have some sort of input and some output. And we tried to do some sort of two additional architectures where you have same these things. Then you have attention, the standard attention. Then you have a transformer. These are separate architectures because like we try to experiment that do we actually need a large language model or simple transformer would do. So to answer this question, is LLM actually useful? We use three sort of like state-of-the-art models, which claim they are state-of-the-art. These are incredibly good models, incredibly robust, have been used in many other papers, and have also came out recently. So the time LLM, one fits all, and CAF. So these are models which use an LLM. We evaluate them, all the past 3-4 models that I described, that their original model without LLM, replacing the LLM with a transformer and attention. We run on 8 very popular datasets like ETTH, which is electricity readings hourly. Then we have weather dataset as well, and several other datasets which evaluate these LLMs on. We find that in this table, what we're trying to report is the number of wins is that we forecast the time series across several windows. That we ask you to forecast either 64 next events, 128 next events, 256 next events, and all these sorts of lengths of forecast. And the best performer in that setting will get 1 win. So across all these settings, across the parameter settings, we evaluate the base model, basically these 3 models, and our architectures of removing the LLM with attention or removing the LLM completely. We found that very simple models, like just removing the LLM, got a majority of wins. And in most cases, the with LLM model failed miserably. Like it actually got 0 wins. Like without LLM model was able to outperform a with LLM model across all the tasks, which was actually quite amazing. We also note that that very simpler models like these have like almost negligible sort of parameters compared to these huge models, worked incredibly well. So this seems that the task of time series forecasting has not yet gone to the large language models. It still exists for traditional machine learning folks. Uh, Now let's let's ask a question. Can we use them, these huge humongous models with so many GPUs, 800 and months of training? Can we use them in real world settings? So in this figure I wanted to show, that on the y-axis you have mean absolute error, basically the difference between the forecasted time and the true time. So what is the error of forecasting? And on x-axis, we have the time it takes for inference. Like, for example, how much time does it take for the model to predict or what the future time series will be. So we found that with LLM models, due to their huge sizes and even the compute nature, they took long time to give you the forecast. But the gains was actually quite insignificant. In most cases, it is actually pretty bad. And simpler models like ours, one like without LLM, other models were incredibly fast. So that means that for some applications like HFT, where you have we have to forecast the time series in minutes, like in even smaller than seconds, then the task of using LLM fails miserably. You cannot use a large language model in these settings. Now let's do one more task, that are LLMs robust to some sort of noises in a time series. So if we try to have a time series, try to like introduce noise or jumble up the events into it. So like, does LLM actually understand what a time series is? Does it actually understand that there is some sequential nature for time series? Does it understand that or not? In this task, we try to understand that like there's different settings where we try to evaluate whether an LLM is able to predict that this is wrong or that is right. This time series has noise or not. And we found that this robustness for LLMs is exactly the same, like for across all models. They don't give you any additional benefit of like robustness. Even the larger models, they don't have any additional benefits. So at least finally we have large language models, we have time series. At least LLM should be good in few short settings, right? So if I give an LLM some samples and ask it to forecast and give them some examples as well of the forecasting, it should work. It should at least work in the setting. So giving the LLM prompt is not the right way. for time series forecasting is what we do is that we take the large language model and our aberrations, and we take 10% of each data set. Then we fine tune the large language model on that 10%, which we consider some few shot. Then we try to forecast for the test set, where we try to check whether, okay, so whether now the large language model can forecast or not, right? This is some sort of a setting for few shot. You have seen the data, you have seen the samples. Does it work now? No. So even in this setting, these large models like GPT-2 and Llama and like we also like are very easily outperformed by very simple tasks. Like you have input, you have instance norm, then the output, nothing specific, nothing special. That works incredibly well, and that can beat large language models easily. So again, we come back to the question: are LLMs actually useful for standard time series tasks, forecasting, which has been studied for years? Is it useful? Again, perhaps not. Like not as of now, perhaps not. So where are we? So through this talk, I wanted to motivate other researchers to focus on this area. That can we use large language models for time series? Since they are going to be popular, and they are going to be the universal user interface. Do we have to work on this area? So current LLMs have a huge difficulty understanding time series. They cannot understand time series that like the way we humans can. They cannot correlate between text and time series, and they lag significantly behind humans. So we have the results for that. The current LLMs actually also cannot work for standard tasks like forecasting, but there have been some results that show that there's some very nice tokenizing techniques worked for time series forecasting. This is the paper called Chronos by Amazon. Uh, but their results we also need to like verify and probably go deeper into whether does it actually work, and what are these sort of techniques or people saying they use. Like, is it actually saving a temporal structure, or is it just completely creating a new time series? You have to focus more on that as well. And there are several research that also like supports our claims that many people have shown that specialized large language models are like lagging behind very simple and very naive supervised baselines. So like as of now, like where are we? Where are we? So we feel that there is a huge need for a data set that should have time series and text, and it should have several downstream tasks like time series classification, time series forecasting, and even time series reasoning. So there's a huge need for that. And note the word current, that like throughout this talk, I didn't want to make a claim that LLMs will never be useful. They will be useful. But as of now, even the large language models like GPT-4 and all are not that accurate in doing things that humans can easily do, or even supervised baselines can easily do. So these are the like set of references and very interesting papers. And like these are in the end the two papers that we discussed in this talk. And now I'm open to questions. Thank you.
Great. This was fantastic, Dr. Gupta. Thank you so much for presenting. Great work. Yeah, feel free, anyone in the panel, to unmute, or if you have a question, ask in the Q&A or in the chat. I'll go ahead and start us off. So you mentioned in the first part of the presentation, just like there's not really good data for this type of task. I'm curious, like, when you were presenting the first part, I was curious, like, although LLMs cannot understand time series data well, like I'd be curious how well they can like generate interesting time series data if you wanted to build like a synthetic data set. Is that something you've looked into? Or just how well it would do?
Yeah, so like in the first part, we tried to create a synthetic data itself. So we asked the LLM to give us synthetic time series. So there was a pipeline for that. The first thing is that if you ask LLM to give you a time series, gives you a very bad time series. Like it's just like static number of 0, 1, 0, 1, 0, 1. It's awful. But if you ask it to give a code for a time series, basically you ask it to give you a Python code or C++ code, and you compile that code, that gives you a very nice time series, which is weird. I don't know the reason for that, but that's what the pipeline is. So LLMs can actually generate very nice synthetic time series, but the moment you take the time series and remove all the text and you pass it the time series again to the large language model, it cannot understand what it generated. So this was a weird result.
Interesting. That makes sense. So like what does that pipeline look like? Like you're generating separate code for each like sample in the data set, or like kind of how does that end up working out?
So we generate different code for each sample in the data set. So the
Interesting.
data set which we have made public, which is publicly available on Hugging Face, it has all that. It has features, the codes, metadata, time series, it has everything. So
We have another question in chat. They ask, can we use time series foundational models forecasting ability to do specialized tasks like anomaly detection?
that is actually a very nice question. So there have been recent works where they use a time series foundation model and they have shown results for forecasting as well as classification as well as anomaly detection. Uh, I don't have a very thorough answer to that because I looked only into forecasting. Uh, but if we go into the tunnel of anomaly detection, perhaps we'll have better insights. As of now, they don't work well for forecasting. Perhaps they might work for AD, but I need to focus more on that. I don't have an answer to that. Hopefully. It would be great if you try and mail me.
That makes sense. We have another question. Can we use LLMs for data pre-processing for time series data? So focus on the data pre-processing step.
Uh, we, I think we can. But the question comes in like, why do we need to use a large language model for that? Like, is it worth using a large language model for pre-processing a time series? Because there are very standard ways of min-max norm or z norm. There are very simple ways to normalize a time series. Do we need a large language LLM for that? I don't think so, but like, yeah, we might be able to do that, but I don't think that's necessary. That might not scale at all. Because if you think of ECGs, the ECGs are taken at ratings of 60 hertz. So for 1 second, we have 60 readings. And if we have a minute of ECG or like say an hour of ECG, like passing that entire time series to a large language model is a huge challenge.
That makes sense. I see we have a panelist who raised their hand. Would you like to unmute, Abigail?
Yeah. Hi. Thanks for the really interesting talk. I
Thank you.
was wondering if you so you talked all everything you're focused on was on time series with just the temporal dimension, and I was wondering if you think that these findings would extrapolate to spatiotemporal data or not exactly, because there is additional information in that and there are ways to incorporate semantic information in that that could be really leveraged in a different way by LLMs.
Okay, so the question is about that findings are mostly in the temporal domain. And do we think that these findings will extrapolate to a spatial temporal domain? So this
Exactly.
actually builds on top of my past experience of working on temporal point processes. So we have worked on temporal point processes as well as spatial temporal point processes. So
Uh-huh.
like based on that experience, I can say that it's if a model doesn't work on time, it works even bad for space and time. But we didn't use LLMs for the spatial domain, but based on my intuitions, I feel that yes, I think that the findings would extrapolate quite easily. So that is based on the fact that your data that you are passing in the sense of space is is a series of distances, right? You don't have a text where you are giving like this is California, this is Bay Area, this is say like Berkeley, and you are doing some analysis near that. If you're not passing data as text, if you're passing data as time series or like a sequence of readings of distances, then yeah,
Right.
that I don't think that will work.
Right. And it might be more, I mean, it's kind of a little bit more straightforward to add semantic information on the spatial level, just like you said, like California or a certain, the context around a certain location
Yeah,
versus adding that kind of semantic and trying to come up with a way to make the temporal information semantic.
yeah. And if you have that data, then you already have a gold mine. So having
Right.
data itself is like the biggest challenge.
Right. Great. Thank you.
Thank you, Abhika.
I'll go ahead and go again. So it was interesting how you tested both like textual input and inputting an image of the time series data. I'm curious if you have any kind of like deeper insights on just kind of like how or like why the performance was different, or kind of how the performance differed in both those input cases.
That actually like motivates me to talk about a very small LinkedIn post I saw some time ago. Is that they actually had a clock and they took a photograph of, and they passed the photograph to a language model and asked it like what time it is. It's a very simple task, right? It's very simple. Any human being can do that. They can look at the clock and say what time it is. In this task as well, that a large language model failed miserably. There are some ones that like Malmo from AI2 that work well, but other models failed miserably. So, like the general intuition would be that these models are black box and no one knows what they have been trained on. The general intuition would be that perhaps they were not trained to analyze time series plots. And like they have been trained on code for time series because there are like millions and millions of time series everywhere. There are some codes for forecasting. All the codes are public as well. So they are trained on generating codes that actually understand how to predict time series, but they have not been trained on, seeing a time series and doing something with it. And this is what the real world is, right? There's no code that simulates the NASDAQ stock price. And I don't think anyone can do that. If someone can do that, he is like some incredibly smart guy. But we don't have that. So that's where I think the difference is. Like they have not been trained on doing that.
That makes sense. I'll give it another few seconds if anyone has any more questions. Otherwise, we can end a bit early. All right, let's call it there. But yeah, Dr. Gupta, this was fantastic presentation. Thank you so much for coming to speak with us. Yeah, great work, and thank you for sharing.
Thank you, Abel, and thank you everyone for coming to this talk. It was a delight to be here. Thank you.